Okay, let's dive in. Forget um, gleaming telescopes spotting faraway planets for a second.
Right.
The very first hint we got, that other solar systems were even out there.
Yeah. Where did it come from?
It actually came from this, well, pretty unassuming old star back in 1917, Van Manen 2.
Ah, Van Manen 2. Over a century ago, and that's the key, isn't it?
Exactly. It became this unlikely starting point for understanding planets orbiting other stars,
Yeah.
even after those stars have, well, died.
And what's really fascinating is that Van Manen 2 is like the prototype for what we now call a polluted white dwarf.
Polluted. What does that mean in this context?
Well, imagine this tiny, incredibly dense stellar remnant, a white dwarf, right? But its atmosphere is surprisingly contaminated with heavy elements, things like iron, calcium, magnesium.
Stuff that shouldn't really be floating on the surface of something with that much gravity.
Precisely. And think about this. Something like 90 to 95% of all stars, including our sun eventually, will end up as white dwarfs.
So this pollution phenomenon, it's probably happening all over the galaxy.
Very likely, yes. It seems to be a common final chapter for planetary systems.
So it's like we're using the death certificates of stars to read the autopsy reports of the planets they used to have.
That's a great analogy, actually. But it immediately presented a huge puzzle.
Gravity issue, right?
Exactly. White dwarfs have intense gravity, absolutely crushing. Anything heavier than helium in their atmosphere should sink incredibly fast.
Like how fast are we talking?
Geologically speaking, instantaneously, much, much faster than the billions of years these things spend cooling down. So finding these heavy elements was a real head-scratcher.
It just shouldn't be there. It should have sunk ages ago.
Correct. So scientists needed an explanation. What's keeping this stuff on the surface or what's replenishing it?
Okay, so what was the first idea?
Well, the initial thought was maybe they just scoop up gas and dust from the interstellar medium, as they drift through space.
Like cosmic vacuum cleaners?
Sort of. But as we got more data, better observations, better models, that didn't quite fit the picture.
Didn't match the composition or the rates.
Yeah, the composition often looked more like rocky material, not interstellar gas. The evidence started pointing towards, well, planetary debris, shattered asteroids, maybe even bits of planets.
Leftovers from the original solar system?
Exactly, the remnants getting ground down and falling onto the star.
So, okay, how does that actually happen? How do bits of asteroid end up polluting the star?
So the leading model now involves gravitational interactions. Picture the white dwarf. Maybe it still has an asteroid belt like our own system does.
Right.
And maybe there are still planets orbiting further out, planets that survived the star's death.
The ones that were far enough away not to get swallowed when the star expanded.
Right. Those surviving planets in their wide orbits can gravitationally perturb the asteroid belt.
Like nudging them.
Yeah, sort of like cosmic billiards. They knock asteroids out of their stable orbits and send them careening inwards.
Towards the white dwarf.
Towards the white dwarf. And when that rocky material gets too close, it hits the tidal disruption radius. Basically, the star's gravity becomes so overwhelmingly strong, it just rips the asteroid apart.
Shreds it.
Tears it into pieces. And that debris, dust, and maybe some gas forms a disk swirling around the white dwarf.
And that disk is the source of the pollution. The material slowly falls onto the star from the disk.
That's the prevailing theory, yes. The disk accretes onto the white dwarf, contaminating its atmosphere.
It's amazing. The white dwarf becomes this, forensic lab for destroyed planets.
Some researchers actually called them astrophysical traps. They trap this material and let us see what the building blocks of planets around other stars were made of.
And it happens relatively fast once the disruption starts.
Apparently so.
Yeah.
Estimates suggest the accretion, the raining down of this material, might only last for, say, less than 1,000 years, which is just a blink in cosmic time.
Wow. And finding these things, has that gotten easier?
Oh, dramatically, thanks to the Gaia mission.
Gaia. The big star mapping project.
Exactly. Before Gaia, we knew of maybe 20,000 or 30,000 white dwarfs in total. Rough numbers.
Okay.
Gaia has boosted that massively. We now have candidates numbering around 260,000, a tenfold increase.
That's huge. So we can study them statistically now.
It's becoming a statistical game, absolutely.
Yeah.
Though they are still intrinsically faint objects, so getting detailed observations on huge numbers is still challenging.
Right. You need big telescopes for long exposures. Okay, so we mentioned surviving planets. How does that work? How does anything survive a star blowing up into a red giant?
It's pretty destructive, for sure. When a star like the Sun puffs up into a red giant, and then later the asymptotic giant branch, or AGB phase, It extends enormously.
Engulfing anything too close. Mercury, Venus,
Uh-huh.
maybe Earth.
Potentially Earth, yes. The calculations suggest planets need to start out beyond about zero point 0.7 astronomical units, roughly Venus's orbit, to have a decent chance of surviving.
So further out than Venus.
Generally, yes. Think orbital periods longer than about 2.4 years. Those outer planets are the likely survivors, the ones that can later perturb the asteroid belts.
Okay, that makes sense. But we are seeing the debris from the unlucky ones, the ones that got too close or got disrupted later. That's where the dust disks come in.
Precisely. We don't just infer the debris from the atmospheric pollution, we can sometimes directly detect the disk itself through infrared light. Back in the early 90s, astronomers noticed some white dwarfs were glowing brighter in the infrared than they should.
Like they had some extra heat source.
Exactly. And that extra glow turned out to be heat radiated by dust particles orbiting the white dwarf, a dust disk.
Ah, the shredded asteroid bits.
Mm-hmm. Space telescopes like Spitzer and WISE were fantastic for finding these. They're sensitive to that infrared glow. We know of over 100 systems with these dust disks now.
100. And is there a particularly good example we can picture?
Definitely. The white dwarf at the center of the Helix Nebula, it's often considered the prototype.
The big eye-looking nebula.
That's the one. The central star, WD 2026-210, has this quite extensive dust ring. It stretches from maybe 35 out to 150 astronomical units.
That's huge. Much bigger than our asteroid belt.
It is. And the estimated mass in that ring is significant to maybe about 1/10 of the Earth's mass, just in dust.
Wow. Is that just from one big event, one giant asteroid getting shredded?
The thinking for the Helix system, and probably others, is that it's likely an ongoing process. The disk is constantly being replenished,
Oh.
probably by collisions between smaller bodies, planetesimals that are still orbiting out there, like a slow-motion grinding down process, constantly producing fresh dust.
A continuous demolition derby. Okay, so when we look at the stuff falling onto the white dwarf, the pollution itself, what's it made of? Is it like Earth?
Remarkably often, yes. The composition strongly resembles bulk Earth.
Bulk Earth.
Meaning the overall mix of elements. Typically, at least 85% of the mass we see accreting is just 4 elements: oxygen, magnesium, silicon, and iron.
The main ingredients of rocky planets like ours.
Exactly. So we're getting a direct sample, essentially, of the raw materials that built rocky planets and other systems.
That's incredible. It's like extraterrestrial geology. Can we get even more specific? Can we tell if these exoplanets had, say, a core and a crust like Earth?
That's where it gets really exciting. The detailed abundances of different elements we measure, they often suggest differentiation happen.
Differentiation, you mean like heavy stuff sinking to the middle?
Yes. The separation into a dense, iron-rich core and a lighter, silicate-rich mantle, and maybe an aluminum-rich crust. The patterns we see in the pollution seem to indicate this was common for Earth-sized bodies.
So we might even be seeing just the crust of a planet sometime.
It's a possibility. Some polluted white dwarfs show compositions dominated by silicon and oxygen, maybe with calcium and aluminum, which looks remarkably like crustal material. Imagine detecting the crust of an exoplanet.
Mind blown. Okay, and I read something absolutely wild, connecting this to plate tectonics. How on Earth?
Yeah, that's definitely pushing the boundaries, but it's a fascinating idea.
Go on.
Some researchers propose that the ratios of specific trace elements, things like calcium, strontium, barium, could potentially hold clues.
How so?
Well, on Earth, processes like plate tectonics influence how these elements are distributed between the crust and mantle. So the idea is maybe, just maybe, if we see certain characteristic ratios in the white dwarf pollution, it could be an indirect sign that plate tectonics operated on the parent body.
That is speculative, but amazing if true. Finding evidence of plate tectonics on an exoplanet via a dead star.
Wow. It's a long shot for now, but it shows the potential depth of information hidden in this pollution.
Okay, so we have dust disks. But you mentioned gas earlier. Some systems have gas too.
A small fraction, yes. Maybe only 1 to 3% of the white dwarfs known to have dust disks also show signs of gas.
How do we see the gas?
Through emission lines in their spectra. Instead of just the continuous glow from the star and dust, we see sharp spikes of light at specific wavelengths.
Light emitted by the gas atoms themselves.
Exactly. The most common signature is the calcium-2 triplet 3 lines close together in the near-infrared, around 860 nanometers.
And this tells us the gas is orbiting.
Yes, the emission lines are often Doppler broadened in a way that's consistent with gas moving in a flat, rotating disk, what we call a Keplerian disk, following Kepler's laws of orbital motion.
And did the gas in the same place as the dust?
Where we have the spatial information to tell, yes, it seems to be co-located with the dust. They occupy the same region around the white dwarf.
Which is strange, right? Shouldn't gas cool down and, condense back into dust pretty quickly?
That's the puzzle again. Yes, simple models suggest gas should recondense onto dust grains on relatively short timescales, maybe months or years.
So the fact that we see persistent gas means something must be continuously producing it.
Precisely. It implies an ongoing generation mechanism.
What could that be?
We're still not entirely sure. Two main ideas are out there. One is sublimation dust grains getting too close to the hot white dwarf and basically vaporizing.
Like ice turning straight to steam.
Kind of. The other idea is collisions. Maybe the dust particles in the disk are constantly smashing into each other, grinding down and releasing trapped gases or vaporizing material in the impacts. A collisional cascade.
But these gaseous disks are super rare, you said.
Extremely rare. We estimate less than 0.1% of all white dwarfs have these detectable gaseous disks, so finding them and studying them is tough.
But Gaia is helping here too.
It is. The sheer number of white dwarfs Gaia finds helps us locate these rare examples. The first statistical study using Gaia data looked at, I think, over 7,000 white dwarfs from an older survey, the Sloan Digital Sky Survey.
Okay.
And within that sample, they confirmed 5 of the previously known gaseous disk systems. It helped establish the rarity more firmly.
And then more recently, using even more Gaia data.
Yes, another study used the larger Gaia data release too. They sifted through bright white dwarfs with good distances and infrared data.
Looking for that infrared excess from dust, and then maybe signs of gas.
Exactly. And they found 6 new gaseous disk white dwarfs. That brought the total known number up to just over 20 at the time. A small number, but growing.
Progress. And were any of these new ones particularly interesting?
Oh yes, a few really stood out. There was WDJ0846 plus 5703.
What was special about that one?
It had an exceptionally strong infrared excess, more than you'd expect from a simple, flat, opaque dust disk. Something more complex might be going on there.
Okay, interesting. Any others?
Then there's WDJ2133 plus 2428. This one is the hottest known white dwarf that has a gaseous debris disk. It's cooking at about 30,000 Kelvin.
Wow, that's hot. Must affect the disk chemistry.
Almost certainly. And then there was a real record breaker, WDG05293401.
What did that one do?
Its spectrum was just packed with emission lines. They identified 51 distinct lines from 5 different elements: hydrogen, magnesium, calcium, iron, and oxygen.
51. That's like a detailed chemical fingerprint of the gas.
It really is an incredible data set for trying to unravel the composition and conditions in these gaseous disks, like a cosmic Rosetta Stone for this stuff.
Amazing. And these gaseous disks. Are they stable or do they change?
They definitely change. For the systems where we have observations taken over months or years, especially the ones where the calcium emission lines look asymmetric.
Meaning the disk isn't perfectly uniform.
Right. Maybe it's clumpy or lopsided. In those cases, we often see the shape of the emission lines change over time.
Oh.
Often it's periodic. The pattern of changes repeats. And it seems to be well explained by the entire emission pattern slowly precessing.
Precessing, like a wobbling spinning top.
Exactly like that. The whole structure, or at least the bright parts of the gaseous disk, seems to slowly wobble or pivot around the white dwarf.
And how slow is slow?
The periods for this precession can range from years to even decades. It's a very gradual wobble.
What causes that? Such a slow wobble.
Theoretical models suggest it's likely a combination of effects. One is general relativity. The warping of space-time near the very dense white dwarf causes orbits to precess.
Einstein strikes again.
Indeed. And the other factor is likely pressure forces within the gas disk itself helping to drive that slow precession.
Fascinating. So, okay, let's pull this all together. We started with this weird observation over 100 years ago. Van Manen 2.
A single polluted white dwarf.
And now it's opened up this whole field. We're using these stellar remnants to probe the final stages of planetary systems, right?
Absolutely. We're learning about the composition of exoplanetary building blocks, getting hints about their internal structure like cores and crusts.
Maybe even spotting indirect signs of things like plate tectonics.
Potentially, yes.
Yeah.
And then we have these rare dynamic gaseous disks adding another layer of mystery about how this material evolves and behaves around the dead star.
It feels like we're just scratching the surface, though.
Oh, definitely. This field is still young and it's evolving rapidly. Missions like Gaia are just going to keep pouring fuel on the fire, giving us more candidates, more data.
Revolutionizing our understanding year by year.
Without a doubt, there's so much more to learn from these stellar ghosts.
It really makes you wonder, doesn't it? If dead stars are revealing secrets about planets this way, what other completely unexpected cosmic clues are out there just waiting for us to figure out how to read them?
Hmm.
Or, thinking about how incredibly rare those gaseous disks are.
Hmm.
What does that tell us? What really specific, maybe violent conditions are needed to create them, keep them going? And what does that reveal about the truly final, dramatic moments of a planetary system's life?
Those are the big questions driving the research now. Really mind-blowing possibilities.